Okay. Still, third week, second subject, buoyancy. This, as you know, I'm a coastal and marine engineer, so this is one of my most interesting topics. And when we, maybe I'll get into it a little bit, but I have discovered many problems with this in coastal and marine. I do a lot of floating things, so or non-floating things as the case may be. I think half my job is fixing other little problems, accidents that happen with this stuff. Okay, so buoyancy. I think you probably all kind of heard of buoyancy before, maybe not thought about it too much. And its lovely little applications, but here we go. So if you need to read the books, there it is, chapter 5 in the book, help you out. So what is buoyancy? So buoyancy, it's a body in a fluid, a thing in a fluid, whether it's either floating or submerged, it's buoyed by the outward force equal to the weight of the fluid displaced by the object. So this is Archimedes' principle. You probably heard of that. I can't even remember the story. He was in the bathtub, something with a king. He's trying to figure out something was pure gold, blah blah blah. So there's probably a nice explanation in Wikipedia if you're interested. But that's the gist of Archimedes' principle is the buoyant force equal to the weight of the displaced fluid. So you can see here, what have we got in our little icon here? There is a 7-kilogram weight suspended. It gets plopped in some fluid. The top of the fluid is in the receptacle is at the elevation of a spout. You drop the weight in there, and it now weighs 4 kilograms. It's got like the force, so you know there's 3 kilograms acting upwards, and 3 kilograms of water got displaced, went out the spout. So the volume of fluid displaced is equal to the volume of the portion of the object that is submerged. Okay. It sounds weird, I know, but it'll make more sense when we talk about it and do some more calculations. So what is the buoyant force? Capital F subset B. It's equal to the specific weight of the fluid, so that gamma of the fluid, times the displaced volume of the fluid. So if you want to know where this buoyant force is acting, it's acting through the centroid of the displaced fluid volume. I know that sounds kind of funny. But if you need to do free body diagrams and that kind of stuff, that's where it's acting, okay? So, okay. Speaking of free body diagrams, here it is. So if you consider a free body diagram of this object held underwater or under fluid, you visualize it by a cable pulling it down. This is just, a cube a cube of some sort. So what do we have here? We look at this cube here. We've got the weight of the object. That's that mg. Which is also the specific weight of the object times the volume. It's also equal to, so the volume of the object in this case, what do we have? Length times width times height, so A, B, H. And now this force is acting down, it's subject to gravity, so it's acting down in our sign convention system. What else do we have? We got F subset W1, so this is the submerged body, right? So what is this? This is the force of the water pressure acting at the sort of the top of the object, and it's acting downward. So remember, it's the pressure times that area, so A, B, and it's acting at that centroid there. So we got 2 forces going down, W, F1, FW1. We've got F subset W2, which, let's look at it, it's the force of the water pressure on the bottom of the object. You can see it's acting upwards. And what's this equal to? So it's going to be equal to that second pressure times that area, which is still AB. And if you break it down, it's going to be equal. Remember we did this before where we added all the pressures in the column of the fluid. So we've got that pressure at 1 plus that weight of the fluid times the height, because we're going from the top of the cube to the bottom of the cube, times that area, that A times B. And that's acting up, okay? Remember, it's acting, the forces are acting perpendicular to the surface, blah, blah, blah. And then we've also got this other force, F subset E. It's the tension in that cable. It's that thing pulling it down because it's submerged, right? So we got four forces: the weight, the force of the water pressure acting down, we've got the force of the water pressure acting up, and we've got this tension in the cable. So because it's statics, sum of the forces equals 0. The joy, again, of being a civil engineer. And you choose up direction as positive, just again, it's that sign convention. We could do whatever, right? So we've got that weight acting down, the force of the pressure at the top of the object acting down. We've got the force of the water pressure acting up, that FW2, plus, and we're going to minus, again, that tension in that cable that's holding it down. So again, the weight is its mass times gravity, and it all has to equal to 0. So let's just have a quick look at those force W1 and force W2. So the pressure of from the fluid at the top and the bottom of the object. So one's acting down, one's acting up. So minus plus. We said the down is negative. So here we go. Minus force 1 plus force 2, force W2. What do we have? Remember, we figured this out in the previous slide. So we've got the pressure from one A to B, and it's negative because it's acting down for force W1. For force W2, we've got that pressure at 1 plus that gamma unit weight of the fluid times the height multiplied by the area, that A times B. So we follow it through, pull it all out, and look at some things cancel. Isn't that amazing? So basically we've got this buoyant force is going to be that unit weight of the fluid times the area, the volume of the fluid displaced, right? As we said. So if we plop those two things back into our original equation, you know, sum of the forces equals 0. We've got the weight, so that minus mass times gravity, plus the unit weight of the fluid times the volume, minus this Fe, this force that's holding it down, okay? So you can also, I mean, we learned this before, right? Where the weight of the object is going to be the unit weight of the object times its volume. And its volume is that A times B, that area times its height. In this particular case, because again, it's a square, okay? And you can take that, because it's fully submerged in the water. No bit of it's floating or exposed, or it's fully submerged. So we put that back into the equation, and we've got the unit weight of the object times its volume, that's the mg, right? Plus the unit weight of the fluid times the volume it got displaced. Again, minus this force that's pulling it up, that F subset E, and it's all got to equal to 0. So look at some things. Can the volume of the object and the volume displaced, wow, they're the same. So we can pull that out, and we've got a little bit more simplified equation. The unit weight of the fluid minus the unit weight of the object times the volume minus this pulling force down is equal to 0. Or another way to say it, so you don't want negatives in front of your forces, that that force that's pulling down is equal to the difference between the unit weight of the fluid and the object times the volume. Archimedes' principle right there, okay? So here we go. We've got this lovely equation. Generally, given our result, that equation that we just spent some slides getting to, now if you have a look at it, if the specific weight of, if the specific weight of the fluid is greater than the specific weight of the object, then Fe is going to pull down in this equation, because again, positive is up. The direction shown in the free body diagram, then the object is trying, so as it's shown here, right? The object is trying to float. If you pulled out that that external force, this Fe, this cube would try to pop back up. Just because, yeah, it's the specific weight of the fluid that it's in is greater than the specific weight of the object, okay? So what's the other thing? If the specific weight of the fluid is less than the object that it's being submerged, it will try to sink. I mean, you can think about that. You drop a pebble in the water, in the fresh water, and it sinks, right? Because, yeah, the density of the rock is a lot higher than the fluid. So there's one other. So we've got one where the specific the density or the specific weight of the object is greater or less than the fluid that it's submerged in. But what if they're exactly the same, right? The fluid and the density of the fluid and the density of the object are the same. It's going to mean that that force is going to be zero. And so what's that called? It's called neutral buoyancy. You might have heard of this before in your travels. That's what it comes to. So that relationship, again, it's only valid if that object is completely submerged, unlike our boat in our in the picture, right? The boat isn't completely submerged yet. No accidents have happened yet. If part of the object is above the water, then the volume of the fluid isn't as displaced is different than the volume of the object, and so then you can't factor that volume out. That volume displaced isn't the volume of the object. Some of it's above water, some of it's below water, exactly like our boat here. So you can work on a general equation that'll work for if it's submerged, if it's floating, all this stuff. You've got minus, because remember the object, the weight of the object is wanting to drag it down. So the specific weight of the object times its volume plus the specific weight of the fluid times the volume that's been displaced minus this external force, it's going to be equal to zero. So this is valid for all cases, partially submerged, fully submerged, okay? The boat hasn't sunk yet, okay? So for situations where there's no externally applied load, so there's no, before we were pretending there was a, a rope, it was holding it down for deriving these equations, but let's pretend there is no rope trying to hold it down. So basically you've got the unit weight of the object times the volume of the object. It's going to be equal to the volume of the specific weight of the fluid times the volume that happens to be displaced. So lots of times, I don't know, you can rearrange it if you care about the volume displaced. It's going to be that ratio between the unit weight of the object divided by the unit weight of the fluid times the volume of the object, okay? Maybe that'll help you think about whether the object's not going to float or not. It's going to float or not, okay? So instead of using this specific weight, this gamma that we've been talking about, you can use, and I think I let it slip there before, you can look at the density or the specific gravities. It's all going to be the same. You can work it out, and it's just this ratio between either the specific weights of the object and the fluid, or the density, that rho of the object and the fluid, or that specific gravity. Remember that dimensionless value, okay? So here's some more words about Archimedes' principle. So another way to think on this relationship is to apply this Archimedes principle. It states the floating object will displace the amount of fluid equal to the weight of the floating object. That's what his thesis over his sitting in the bathtub, okay? Any body completely or partially submerged in the fluid, and remember the fluid can be gas or liquid, at rest, so it's not moving, sum of the forces equals 0, is acted upon in an upward or buoyant force, the magnitude of which is equal to the weight of the fluid displaced by the body. So if we had the specific weight of the object, it's going to equal to the specific weight of the fluid, and remember that's that neutrally buoyant case. Then the volume of the object has to be equal to the volume of the fluid. So it floats. It stays in any given position in the fluid, and it's said to have neutral buoyancy. It all comes around. Okay. So here's a problem to try. Okay. A ball is tethered on a lake floor, so again, fresh water, and has a mass of 400 grams. The tension on the wire is measured, and it's measured to be 30 newtons. What's the volume of the ball? So we've got specific gravity of the water is 1. Life is good. And you've got, so that it's all fresh water at 4 degrees C. So you know the specific gravity, you know the unit weight, you know the density. It's also written right there. Give it a try. Then on Wednesday, we'll figure this out. So here's another one to try. It's a boat with an anchor. I love these little doodles, they're fun. So the weight of the anchor is 450 newtons. Holy moly. The volume of the anchor is 0.015 meters cubed. What tension is required to hold up the anchor? So it's not resting on the floor, it's just kind of hanging out in the water there somewhere in the water column. And this happens to be seawater, okay? So you got to figure out that force that's going up. Give it a try. We'll do it on Wednesday. Here we go, a block of styrofoam. This is almost my lot in life right here. Has a density of 200 kilograms per meter cubed. Sure. Its dimensions are the height is 1 meter. The length of it, A, is 3 meters. And the width of it is 3 meters. And it's floating in fresh water, so remember, you know all the properties of fresh water, its density, specific gravity, specific weight. Now you find X. So basically, what percent, so find X. And that is, if you guys care, is called a draft. So it's basically, it's the length of the height submerged in the water, the draft. The other portion, if you care, that's out of the water is called the freeboard, okay? My life is, a lot of my job is trying to figure out that freeboard. It's usually the freeboard that's specified. They want whatever they want to service boats or service whatever. So find X, the draft, and what percentage of the volume of the object is below the water, okay? So a little bit, a couple extra steps, you gotta find a percentage. You can do it. I know you can. Okay, week 4 in a nutshell. And we'll do all these problems on Wednesday at 10:30 over Collaborate. Excellent, you guys.